Look at this brand new image of the black hole M87 star, just recently released by the European Southern Observatory. A lot of you might remember this particular image of the black hole M87 star, which was released by the AHT back in 2019. Now, after 4 years, we have imaged the same black hole again. What is so special about this time? Hello and welcome everyone to another brand new video. And in this short video, we will take a tour of this new image of the M87 star that was released by the European Southern Observatory in collaboration with the GMVA, ALMA and the Greenland telescope. So the reason why we have another image of the same black hole almost 4 years later is because this particular image is showing us black hole along with its emission jets, which has been seen for the first time, and this is a direct image of that entire system together. The 2019 image by EHT was different, as in we were just imaging the black hole's shadow, but this particular image sort of captures the entire surrounding of the black hole and also its strong, powerful jets, as you can see in this particular image. The reason why we see all the jets and more of the surrounding region of the black hole is because this particular image was captured at a much different wavelength as the one captured by the EHT. So the image that you see has been observed at 3.5 millimeter wavelengths as compared to the 1.5 millimeter wavelengths that was observed by the EHT. Now you might ask, why are we observing at a slightly higher wavelength of 3.5 mm? The reason is because at these wavelengths we can also see the emission features of this particular radio source. The radio source is of course the black hole and its surrounding accretion disk, and this slightly higher wavelength allows us to sort of probe not only the surrounding accretion disk but also the jets that this particular black hole is producing. Not only that, astronomers have also found that the surrounding region of this particular black hole is almost 50 times larger than the one imaged by the EHT. So at this particular wavelength we can actually see more stuff that was not seen at 1.3 mm. By now I have probably stated this many times in all of my videos, is that we want to observe a particular target of interest at different wavelengths of the electromagnetic spectrum. Different phenomena emit light at different wavelengths and different frequencies. So by covering a particular astronomical source from all different frequency ranges, we can basically gather much more information than what we would do from a single source. So think of this study as a complementary study to the one by EHT. Okay, so now at the very beginning I mentioned that this was done in collaboration with the GMVA, the ALMA and the Greenland telescope. GMVA stands for Global Millimeter VLBI Array. This, as the name suggests, is another group of telescopes doing very long baseline interferometry, or VLBI. I have actually made a dedicated video on VLBI which will be linked above. I highly recommend you guys to sort of take a look into this video, as I explain VLBI in much more detail in that particular video. But what this technique actually does, it basically combines telescopes located at very large distances, often like from one continent to the other, which basically synthesizes a huge telescope which wouldn't be possible to build practically. And this basically allows us to achieve extraordinary resolution, allowing us to sort of study these distant black holes and its surrounding system. So the GMVA network actually has participating stations in Europe, East Asia, North America and Mexico. Finally, we also have ALMA in the South American part. In Europe, we have the flagship telescopes like Effelsberg. In East Asia, we basically have the Korean VLBI array. In North America, we have the VLBA and sometimes the GBT as well. In Mexico, we have the famous Large Millimeter Telescope, or LMT. And finally, we have ALMA, and ALMA plays an extremely important role in sort of giving the final touches to this particular image. So oftentimes when we study some astronomical sources, for example black holes, what we actually do is we actually combine our theoretical models with the real data that we have collected. By that I basically mean we try to fit the best models that we have, which sort of encapsulates all the physics of that particular system, and we try to fit all of those to the real data. The reason why we do that is because we want to extract different parameters from that particular data. A simple example of this would be the straight line model. So we know that the straight line can be mathematically represented as y equals to mx plus c. We can perform different experiments in the real world and try to extract some critical parameters from those experiments. For example, if I'm trying to measure the resistance of a particular wire, I can actually give it a voltage and measure the current that passes through that wire and take a series of measurements varying that particular voltage. And once I have all those data points, I can actually try to plot a straight line and extract the resistance from this using my y equals to mx plus c model. So basically the same principle is followed in astronomy as well. If you have a model which sort of describes a particular system, you try to fit that model with your real data and extract certain parameters out of them, which in the case of a black hole, as you can see, astronomers have actually fitted the model of accretion disks around black holes with this particular image that they have taken, and from there what you see is this particular new image shows a higher inflated radius, almost 50% higher than the one taken by AHD, revealing that more gas is actually flowing in this particular black hole. Now, just to give a quick background of what this glowing accretion disk actually is. So black holes are extremely dense objects, so much so dense that in order to escape the gravitational pull of that particular object, you need a speed greater than the speed of light. So the escape velocity of black holes are actually greater than the speed of light, hence light cannot also escape. So what happens if you bring such a dense object in an environment where there is a lot of gas and dust? So a lot of those gas and dust will start funneling towards that black hole, and as a result there will be a lot of collision between the particles of the gas, and this collision will actually heat up those particular gas, and once they're heated up, they start emitting at different wavelengths of light. So in astronomy, we broadly have two major sources of radiation, the first being the thermal sources of radiation and the second being the non-thermal sources of radiation. Now, thermal sources of radiation, as the name suggests, is caused due to the thermal motion of that particular object. So almost everything in this universe radiates in the electromagnetic spectrum. So for example, us humans, we radiate in the infrared, as you've seen in all of this video. Non-thermal sources of radiation is, as the name suggests, is caused by not the random motion of the particles inside that object, but actually caused by external fields and forces. So in the case of a black hole accretion disk, non-thermal sources of radiation are mainly synchrotron radiation. And synchrotron radiation is caused when electrons are accelerated at extremely high velocities in a particular magnetic field. And at those conditions, they start radiating away in synchrotron radiation, which is actually observed around black holes. And these synchrotron radiations are then picked up by radio telescopes, giving us a lot of information about the surrounding of the black hole. So I'll end this particular video here. This was a short video sort of going over this particular new image. This is basically a new perspective to an image that we already had before, and giving us a much bigger picture of that particular image. Again, if you're new to this channel, I am Mayuk. I am an astronomy grad student and I love making content around astronomy on YouTube. If you enjoyed watching this particular video, please consider subscribing and leaving a like on this video. I'll catch you guys in the next one really soon.